Hello, check. Coming? Thank you very much. So I'll talk about some classical problems in graph saturations. Okay, let's begin with the definition. So what do we mean by graph saturation? A graph G is called F saturated. F is also some graph. If G is F free, and adding any edge to G creates a copy of F. No, not induced free, F free. There is no subgraph of G which is isomorphic to F. And we care about this function called sat n comma F, which is defined to be the minimum number of edges. So EG denotes the number of edges in G in a n vertex F saturated graph. So let's do a small example. So for example, sat n comma k1 comma 2. So k1 comma 2 is just this graph. This is n over 2. Okay. So just like saying this because it would be easier to later see how to obtain upper bounds and lower bounds. So upper bound generally comes from construction for saturation numbers. So you can see if you take a perfect matching that achieves this number, and lower bound, to prove a lower bound you need to do some proof, like you need to show that for all n vertex F saturated graph the number of edges in your graph is at least this. So for example here you can say that there can be there exists at most one isolated vertices. So from that up in such graph in n vertex k1 to saturated graph, from that number will follow. Okay, because if you have two isolated vertices then you can join the edge between them and you don't create any k1 2. Okay, so let's now turn our attention to this first result proved in this topic, Erd H-Hajnal-Moon. It was done in 1964. So they proved that sat n comma ks is exactly this number s minus 2 times n minus s plus 2 plus s minus 2 switch 2 for n greater equals to s greater equals to 2. And the unique extremal example is this graph. You have this ks minus 2 and you have this independent set. Let's write it this way, like k bar means the complementary of the graph n minus s plus 2. So this is basically just an independent set and you take the join of them, like add all the edges in between. You can see this is ks saturated because if you add any edge here then you create a copy of ks and the number of edges in this graph is given by this number, right? Okay, this was nice, and we also have a complete characterization of the extremal graph. Now recently there have been a trend of studying generalized version of different extremal problems, including saturation problems. So people cared about this function called let's write definition again. This function which says sat n comma h comma a, and this is defined as the following: minimum number of copies of h in an n vertex F saturated graph. So by this definition you can see that this number is nothing but just sat n comma k, right? It is just counting number of edge. Okay. So the first problem, first natural problem which comes to mind is like, can we generalize this classical result? And what we so first observe that if we try to look at number of copies of kr in a case saturated graph, we still get some upper bound which comes from this same graph. So to get an upper bound we need to count the number of copies of kr here, right? So what is that? That is just you can choose one vertex from this independent set and r minus 1 vertices from the clique. That number is something like s minus 2 choose r minus 1 times n minus s plus 2, plus also the number of cliques of size r inside that s minus 2 clique, which is s minus 2 choose r, right? So this number, this upper bound comes from this same construction, and it has been shown by Kritschgau, Methuku. So Methuku was research senior researcher here before, Tait and Timmons. By them that this number is also like is linear, like lower bounded by some linear function, and their lower bound was there was a factor of r minus 1 there basically, and they also conjectured that this is indeed the right answer. So what we managed to prove is, and of course, like when we are talking about this function, we are assuming that n is greater equals to s is greater equals to r, right? Because otherwise the problem doesn't make sense. Like, so we managed to prove the following for s greater than r greater equals to 2. Okay, I guess this is s greater than r because when it's Ks saturated, the number of copies of Ks is 0, right? So yeah, we can do that. So for this, there exists a constant. There exists a constant in r comma s such that for all n greater equals to n or s. So basically for large n of n, that's all it says. Set n comma kr comma ks. This is basically the same number, r minus 1, n minus s plus 2 plus s minus 2. So we proved this conjecture for large n of n, and we also have a stability result which says the following. There exists some constant cr comma s such that the only Ks saturated graph with at most this number set n comma kr comma ks plus a linear factor cr comma s times n with at most this many copies of kr is this unique example. Let's just write it in this way: ks minus 2 join kn minus s plus 2 bar. Okay, so even if we allow few more copies of kr, we still have like this only extremal example. We don't have any other graph which is case saturated, of course in vertex. Let's be precise, in vertex, case saturated in vertex, and number of copies of kr is like little bit more than the saturation number. Okay, and of course it can be shown that there exists some constant for which this fails, and it will be an interesting open question to pin down this. This is an interesting open question. Find best possible, like find maximum CRS, which you can write here. Find best CRS. Yeah. This is a positive constant. Very good.
Find the negative one.
Sure. Yeah, thanks. Okay. Interesting. Okay, so in this talk, I will give a proof case of the following asymptotic version. S greater than r greater equals to 2. We have set n comma kr comma ks equals to n times s minus 2, which is r minus 1 minus small of n. this is just an asymptotic version of what I just stated there, because like this is the main term is this n times s minus 2 choose r minus 1, right? I mean, if you want to see for a bit, the main term here is n times s minus 2 choose r minus 1. Okay. Let's see how it goes. So assume G is a n vertex f saturated not f saturated k saturated graph with this many k's. Okay, like this is some graph which has the lowest possible number of k's. Now define this set E1, this subset of E, which contains all the edges containing all the edges which is contained in a copy of kr. So if you look at G, some of the edges are in a copy of kr, some are not. So E1 denote the edges which are in a copy of kr, and E2 the rest of the edges. Okay, so note that all the edges in E1, they are somehow participating in the count of number of k's, right? And the edges of E2, they are not really contributing to the number of k's. They are just somehow blockading the space, right? So somehow you need to treat these two edge set in different ways, like okay. So here is a very simple claim. By the way, I forgot to mention that for this Erd H-Hajnal-Moon result, so the first time when it was done by some inductive argument, which is very simple, pretty simple, and later it has been extended to some weak saturation and some like other notions by Bolovas using like a very beautiful result like set pair family, which is independently very interesting and found many applications in other areas as well. So let's look at this claim. So every edge of E2 would not be in a copy of Ks even if some edge were added to G. So suppose this is our graph G, and let's say we added so this is some edge E which is in E2, and let's say we add some edge E prime, and let's say we found a copy of Ks which contains both E prime and E. Okay, so this cannot happen because if this happened, what does this mean? This means so this is a copy of Ks, right? All the edges are present here. Now if we throw this vertex out, we found a copy of Ks minus 1 containing the edge E, right? But we know that E cannot be in a copy of Kr, right? We know, remember, E cannot be in a copy of Kr, right? But here you can see that E is in a copy of Ks minus 1, right? And of course, this is true because R is less equals to s minus 1, right? So that means E is in a copy of Kr, which is a contradiction. So this is a very simple lemma, simple claim. So what does this imply? This implies, okay, so let's write here like, you know, a very simple consequence of this, that adding any edge in E complementary, basically it just says, like, you know, you are adding some edge which is not present in G, creates a copy of Kr in G1, where G1 is V comma E1, right? Question?
Creates a copy of KS.
Yeah, that's very correct. I mean, we are looking at Ks saturated graph, so yes, it should create a copy of Ks. Thank you. Okay. Now define this set capital A, which is a set of vertices whose E1 degree, or in other words degree in G1, is small. I will like, you will see why we consider this particular function, but for a moment, so we are so if you for example look at the extremal graph, A is basically the independent set, right? Wait, what am I saying? Yeah, right. A is the independent set because they have like small degree, right? So if we look at this set capital A, we claim that size of A is n minus small o of A. It's very easy to see why. The reason is, what is the size of E1? The size of E1 is at most R choose 2 times sat n comma kr comma ks, right? So E1 contains all the edges which is inside at least a copy of kr, right? So this is the number of copy of kr inside G, and in each copy of kr you have at most R choose too many edges. I mean, exactly R choose too many edges, right? So the number of edges in E1 is at most this, and we know this is linear because we already have the upper bound on this saturation number, right? So now you can easily see that this, the number of vertices whose degree is whose G1 degree or E1 degree is more than n power 1/3 should be at most this, right? It's just some simple, like, you know, counting argument, and basically we are done, right? What we claimed. It makes sense?
So we are already assuming that the saturation number is n.
At most n. So right now we are trying to, because of the example, exactly. Yeah. Like we are right now trying to prove a lower bound, like, because upper bound is already known, right? Like, because of the example, like this observation, yeah, because of this. Okay, let's try to find how I want to write it. Okay, let's do this. Oh, did I make it inconvenient? Okay, maybe let me move on to the other side. Actually, I think that would be better. Okay, let's go to this part. Okay. Now what do we know? Okay, actually, I should continue here. It would be easier for me.
So, the set A complement is the complement of A with respect to V or with respect to
A complement is, what I mean by A complement is
set of vertices having degree larger than
V minus.
Oh, right, yeah.
This is what I meant.
Yes, okay, yeah.
Yeah.
There's no particular meaning to the one vertice.
For now, there is no meaning, and also for the sake of argument, like any function which is small o of n to the power half would work basically. Okay, but it cannot be higher than that. But for time being, there is no meaning. Okay. Now notice the following thing. So now, what is the structure we have so far? So we have, like, something like this big set capital A, and this is the A complementary. We have like, all the vertices here have at most some small even degree. By small I mean this number. Okay, now imagine the following scenario. Okay, let's just write it as a claim again. If UV, which are two vertices here, okay. Let's say UV belongs to A, UV does not belongs to capital E, UV is not in the edge set of G, and UV do not have a common neighbor in capital A with respect to, so let's say in graph G1. So now if we look at graph G1, UV do not have a common neighbor in capital A. So for example, there is no such vertex, okay, but in G1, okay, I'm like sometimes switching between G and G1, so hope that doesn't cause inconvenience. So if this is the scenario, then what happens? If we add this S between UV, we create a copy of KS, and that copy of KS should have S minus 2 vertices from A complementary, right? That's because essentially this claim, right? Because we said that adding any S in E complementary creates a copy of KS in G1, and we know that they don't have any common neighbor in G1 inside capital A, so it should be in A complementary. So let me finish this. So if we do not, then adding UV creates a copy of KS with S minus 2 vertices from A complementary. Okay. What does this imply? This implies number of copies of KR containing V is at least, so what's the picture now? So the picture is we have this UV and we have this S minus 2 vertices here, so that this is a complete graph and also this is a complete graph, right? So the number of copies of KR containing V is at least, if you pick any R minus 1 vertices from this S minus 2 vertices, you will get a copy of KR, right? So it's basically the countings are similar to the extremal configuration. And now if you can somehow argue this for all V inside capital A, then you will get the asymptotic bound, right? Because we already found the coefficient S minus 2 is R minus 1, and then it will be multiplied by the size of capital A, right? Is there any question? So the only task remaining is to show that for u belongs to A, you can there exists V in A such that star holds. Star means like the hypothesis of star holds. Right? If we can show that, then we know that every V is inside at least this many copy of KR, and also but from the argument there is no double counting because all the KRs have exactly one vertex from this capital A. All the KRs we are counting. And this is true because suppose this is capital A and we have a vertex U. So if you look at the neighborhood in G1, there are at most n power 1/3 many vertices, right? And all those vertices have at most n power 1/3 many neighbors. So this total size is at most n power 2/3. So here basically you need this particular function. So that means there are many neighbors, many vertices in capital A, for which you know U and V do not have a common neighbor in G1. And basically there are some other arguments. You somehow need to make sure UV is also not an edge in the graph G, and like you know if you can find such V, then everything works. Is it clear? Question?
So when you say number of copies of the evidence, do you delete it in apply induction? So
I'm not doing any induction here. So what I'm saying is number of copies of KR containing V is this, and so now what is your question? Is it like how am I completing the argument? So I'm just adding up all the copies of KRs counted this way. Like for all V in capital A, I have number of copies of KR, at least this, and I'm just adding up. So you might be confused maybe because there might be some double counting, but double counting doesn't happen because in this step when you are counting a copy of KR, all the KRs look like of the following: one vertex from A and R minus one vertex from A complemented. So you can never have double counting.
Why do you have to show that there's no? Can there even be an edge in G? If you choose any of these B's, could there be an edge in E2 with that? Because
that can be, right? You cannot just discard.
you just showed if U and V don't have a common neighbor in A, in the graph U1, then adding UV creates a copy of K.
Yeah, but adding UV means like if UV is originally an edge in G, then you cannot add that UV, right? So when I say this, that means adding like this some edge is in E complemented. Like it cannot be an edge in either of E1 or E2. So that's like you know. So okay, the way I have said it here, it's not really true. So the thing is for almost all. So for almost all. Okay, for almost all vertices in capital A, this holds basically. So there can be some vertices which has large E2 degree, but like you know there is some like you know careful analysis, and that part is like pretty straightforward because you know that in your graph there is no copy of KS, right? So you know your graph, like for most of the vertices, of course you know you will have enough room to accommodate some vertices, right? Like your graph, even if you think about like to run, like if you don't have a copy of KS in your graph, like you know like you know the complementary of the graph should be dense enough, right? So like you know So the you know I avoided doing those like details because it's kind of messy. It doesn't like it's pretty simple to do, but it's just some work you need to do. Okay. Okay, so if there is no more question, I'll move on to the second topic, like on graph saturation, but some different problem. So now I'll talk about behavior of saturation function. Let me start with the following theorem. Which says for a graph on S vertices, this number sat n comma f. So I will no longer talk about the generalized saturation function. From now on, it's just sat n comma f. This is at most sat n comma ks, which we have already seen to be linear. Okay, this is pretty simple to prove, which I'm not going to do. So we know that saturation function is always at most linear. And now I'll give some example showing that how this saturation function lacks monotonicity. Okay. So for example, in extremal function, so extremal function is basically you have x n comma f denotes the maximum number of edges in an n vertex f free graph. So for extremal function, there are these monotonicities. If you increase the value of n, this is like non-decreasing, and also if you have something like this n comma f, if f is a subgraph of f prime, then this type of results hold. But this type of results are not true in the context of saturation function, and that's one of the reasons why inductive argument doesn't really work in proving statements in saturation. So let me just quickly give two examples. So if you look at if we look at monotonicity in terms of the first parameter, sat 2k minus 1 comma p3. P3 is just the path with 3 edges. This is k plus 1, and let me just write this way, which is greater than sat 2k comma p3. So for this sat 2k minus 1 comma p3, the extremal example would be something like you have something like this, and for this it will be okay. And there exists connected f subset of f prime such that sat n comma f is other way, like it's strictly greater than sat n comma f prime for large n. Okay, and let me give a quick example. So you can take f to be let's say a star, okay, k1 comma d. This is your f, and take f prime, just subdivide one of the edges there, like which looks like something like this. Okay, this is f prime, and an easy way to see why this this inequality holds is the following. So in this graph, if you have a F saturated graph, then that graph should have minimum degree 2. Not really, but like most of the vertices should have degree at least 2, right? So like if you think about it, I will leave it as an exercise. Okay, sat n comma k1d should be, you know, something like I want to say d minus 1 over 2 times n, something like that. Okay, but for this graph, there is a very easy easy F prime saturated graph. If you just take union of this type of graph, adding any edge would create a copy of F prime. Yeah, and this. Sorry, what?
You wouldn't take a union of k-plots?
Okay.
I mean,
Yeah. You are absolutely correct. So I think just adding one more. Yeah. Just doing this. Yeah. You are right. So because like if you add this type of edges, then there will be problem. Yes. Yeah. You are absolutely right. So yeah. So just you don't have to think about this a lot, but like there are such examples. So to to still give a theory about like how smooth the behavior of like saturation function is, to use a conjecture the following. So this is a conjecture. Which says for every graph f, this limit n tends to infinity, sat n comma f divided by n exists. Okay. And I'll write the closest positive attempt, which is like almost nothing, but I'll still write to show how this literature is almost nothing is known. For every graph f, if this lim_inf exists, lim_inf n tends to infinity sat n comma f over n exists, then limit n tends to infinity sat n comma f over n exists, and there is some additional information, and this is equal to 1 minus 1 over p for some integer p. Okay. Yeah, lim_in. This is lim_in. Okay, so such results are known. Okay. Let's now talk about the negative direction. Okay, so so far, like from the discussion, you might think like yeah, this should exist. Even maybe it's very difficult to prove such result, but it should exist. So let me show you some negative result. Like this is not disproved either, but like some progress in negative direction. Let's consider the saturation function of a family of graphs. Okay, so it works very similarly. Let me just give you a quick definition. So let's say f is a family of graphs, and I guess let's just talk about finite families. So this is a graph family. So I think there are also theories about like infinite graph family, but I'm not aware of those. So for finite graph family, let's say a graph G is curly F saturated if G is F free for all F inside curly F, and adding any edge to G creates a copy of of some graph in F basically. Okay, and similarly define sat n comma F. This is the minimum number of edges in G such that G is in vertex F saturated graph. Okay. So what Pikurko showed is the following. There is a graph family of size 4. There exists a graph family containing 4 graphs. Such that this limit n tends to infinity sat n comma F divided by n does not exist. Right. So also if you can prove for some k, then it's true for anything higher than k as well, because you can just add some stupid graph in the family. Okay, just not so if you have so for example before this I think the series of result was first he came up with some graph family containing infinite graphs for which this doesn't exist, and later then he improved it to some finite number, but the so there is a there is an infinite family of graph families, and they have sizes 4, 5, 6 ... Okay, and what I am trying to say is if you have a family for 4 graphs, it's not easy to come up with family of 5 graphs. Okay, let's now briefly say what I managed to did here. I'm sorry? F is finite. This F contains 4 graphs, so of course it's finite. Yeah, containing 4 graphs. Okay.
So when you say the limit doesn't exist, so we already know that limit is bounded, right? I mean the ratio.
Yeah. So you mean it's oscillate? Yeah. It's oscillates. Yes, exactly. So you will see. I mean, yeah, we have enough time to. I will give some case on that. One of the example also. Okay. I think so. I don't know otherwise. I'm pretty sure that's the only type of counter examples. Okay. Anyway. So what we managed to prove is the following. There exist infinitely many graph families of size 3 so that it doesn't exist. Okay, the same conclusion basically. The limit doesn't exist. That's right. The limit does not exist. Okay. So yeah, it's okay. Yeah. Okay. I will explicitly draw the graph, so you don't have to So consider this graph VM. You can pick M to be anything, and that is infinitely many. So you have this Km, and from one of the vertex have 2 neighbors outside. That's first graph. The second graph is looks like dumbbell. You have this km and bmm, and the third graph looks like the following. This is the km, and you have two vertices which have some outside neighbor, and let's name it lambda m. Okay. So, but for this family, basically the limit doesn't exist, and let me quickly sketch why that is the case. So, if so, we care about sat n comma f, right? So this limit. So if m divides n, then what can we do? We can take just the disjoint union of km's. So this is f saturated, right? Because if you add any a's, that creates bmm, and you can check that this disjoint union of km's don't contain any of those graphs. So we have this sat n comma f is at most n over m times m choose 2, right? This is just the number of edges in the construction. Okay. Let's say case 2, when m does not divide n. Okay. So when m doesn't divide n, then of course this simple, like, you know, the reason is you cannot have such nice construction, of course. And let me give you a brief idea, like, you know, why you cannot, you know, do, you know, why you need like significantly more number of edges than this construction. So suppose let's try to imitate this type of construction. Okay, this is, I'm not going to give a proof here because it's like, you know, not like I don't have enough time to do that, and also the proof is like kind of messy. So you have like let's say you have some disjoint union of km, and of course there will be some leftover vertices, right? Let's say the size of this is smaller than m or whatever. First of all, note that no two km can intersect each other. Let's actually say that if you have two intersecting km's, then you will have either Vm or lambda m in your graph. Okay. If there are like depending on, like, so there can be situations when one of them is there but the other is not there. Okay. Sure, yeah, m is at least 3 probably or something. Yeah, of course. Anyway, so you have like some leftover vertices here, right? So from this leftover vertices, you should have at least one edge from to each of these km's, right? Because if you don't have, suppose this is a copy of km, and from this leftover vertices you don't have any edge, then adding any edge would not create any of this basically, because to create one of these two, you need to have at least one of them present already, right? Like again, I'm just like, you know, saying a rough idea, not like, you know, giving a proof, like so, you know, somehow like if you, so this turns out to be the worst case, like if you, like, again this needs some proof but I'm not doing. So then, like, you know, you can show that somehow so if you count all these edges, you'll have like something like plus n over m, and if you, like, you know, look at the ratio, it oscillates basically. And yeah, I do not know any example where the proof, you know, doesn't, like, you know, doesn't go with, like, you know, this type of modulo class analysis. Yeah, that was what Casey was asking before. Anyway, let me also tell you the following, that for this two-judge conjecture, it's not even known for simple graphs like cycle. When f is a cycle of, like, let's say fixed number of vertices, then we don't know if this ratio exists or not. There are some, like, you know, good lower bound or upper bounds, but like it's not known if it exists, that limit. So it will be interesting, you know, to try to settle this two-judge conjecture, and also like it will be interesting to see if there is some graph family of size 2 which like violates this like for which this limit does not exist if there exists such graph family. So by that I am done, and if you have any questions I'll be happy to answer. Bipartite, yeah, I mean there are some bipartite. I mean, were you there when Dashi gave a talk? So that he was talking about bipartite person. So you can like talk about like such problems sat knn, comma like KST for example. Here like the problem is similar. Like the host graph is now bipartite graph on like n vertices in both sides, and what is the minimum number of edges, so that like you do not have any KST, and adding any edge would create a copy of KST. And when you are adding edge, you are adding some edge like across the bipartition. Yeah, there are such problems, and so there are other problems as well, but again like proving like exact results or asymptotic results are not so easy for this type of problem. So yeah.
So for me, this family discussion you had with the second problem maybe more naturally fits in with this 3-parameter saturation function. So is there anything if you replace there the f with the family?
F with, yeah, you can do that, of course. So
something interesting there.
so of course the problem becomes even harder, because here you are like trying to count like some general graphs. So it's also known that it's not known, but it can be seen from the argument used by, okay, why did I write it? I somehow wrote it's always linear. So from this from the same argument as them, it can be shown that set n comma kr comma f is also linear. Like if you are minimizing copies of kr, and so this also motivates us to like replace this sat n comma f by sat n comma kr comma f in this two-judge conjecture, and like ask the same question. But I don't know, it might be even easier, but like I thought about this problem for like maybe less than half an hour, and I thought it should be harder than the edge case, and didn't even make sense to try more.
So in your theorem here, if you just have the graph family consisting of the second two graphs, so the dumbbell and
For any two graph, if you take the ratio exists. Yeah, that's one of the question I get whenever I try to present this. Did you try this? Yeah, I tried. No, I understand. Yeah.
I know one part of it. I know that you wouldn't have the proof of the same result with some subset.
Oh yeah, that's a good point. But no, it exists basically. Yeah, it exists exactly.
Between the two graphs, do you think
So
the limit?
of course what I believe doesn't matter, but what I believe is for two graphs it probably doesn't exist, but for one graph I think it should exist. This is what I believe, but of course it might be otherwise.
For this proof, you define the set E1 and E2, and I was trying to think, is it possible for E2 not to be empty in a sense? Like if you have a saturated graph for KS?
So I mean, like if it's empty, then if it's non-empty, then of course the count of the number of KR would be like very high, because you remember, because of the stability result we have, like even like that's the unique example, right? And also if we even allow little bit more copies of KR, still you have the unique extremal example. So if E2 is like non-empty, then
Yeah, no, I understand that your proof is like I just couldn't think of any way to construct a graph where this set A2 won't be empty.
Oh, okay, that's what you meant. Like,
Yeah.
you want to have an example. Like, you don't care about the number of copies of K.
Just
Okay.
whatever you can get a saturated example without this.
You can have pathological example, I'm pretty sure, but okay, that's a very good question. I have never thought about it. Yeah.
Like if you have a triangle, you have a K4 free graph, which is a saturated K4 free graph. Is there an edge which isn't in any triangle?
Which isn't in any triangle.
Is it possible?
It's a very good question. So what about yeah, I don't know. I don't know actually. I need to think. That's a very good question. Yeah. For small, yeah, probably when you ask this question, you meant for large n, I guess. Like for small n, I think, yeah, as Sangil said.
Do you have an example for small? I mean, yeah, I'm more interested in the large end, but still could be useful to understand the small thing. Yeah, I mean, it's just, yeah.
Yeah.
If you don't already know, it's probably
But with the small
not
n,
a-
from strength configuration,
Right.
yeah.
any further questions? So if not, let's thank the speaker again.